Good afternoon. My name is Eugene Bryce of Bryce Energy Services, and today I'd like to give a little presentation called Electricity for Businesses. The idea is to have a broad discussion about issues relating to electricity use for a business, starting with some technicalities of how electricity actually gets to a business. Then we'll talk about energy bills and some new product innovations. So, objectives from this presentation. By the end, we should be able to describe what electricity is and how it's delivered, key technical terms used in the electrical industry, understand a typical business energy bill, and look at some new technologies and developments in the industry. So, what is electricity and how it's delivered? So, electricity, what is it? Electricity is a form of energy, and energy gives you the ability to do work. So basically, it's one form of energy that you and your business use for lighting. So you convert electrical energy to light energy, or you'll convert electrical energy to heating energy if you have electric heaters, or any other mechanical energy, perhaps electrical motors. So, Albert Einstein, energy cannot be created or destroyed. It can only be changed from one form to another. So, how is electricity created? Given that we have to have another form of energy to convert to electricity, which in turn then converts to light energy. So this is a very basic electrical generator. What we have is an electrical wire connected to a light bulb. So this is our wire, our light bulb, and it's placed between two magnets. And what happens when we turn this handle is that we'll actually generate an electrical current which will light up this light bulb. Actual generators usually have the magnets moving or the magnetic field moving, and the wires are stationary. But for our little example, it's sufficient to say what we do is we rotate a machine, and this machine could be rotated by wind, water, but in most cases in the UK it's steam driven. So a steam driven generator. So where does the steam come from? Boiling water. How do you boil the water? Well, it could be nuclear fuels, burning coal. But however the cables are turned, it's within a magnetic field, and that's what generates electrical current to light up our little light bulb. This is a more complicated electrical generator, but same principle applies. Instead, we have our magnet moving within the machine. So this is rotating. And we have, instead of just one wire, we have 3 wires. And each of these gives us what we call a phase. And we'll look at that later as to what it means in practical terms. The next machine that is worth a mention is called a transformer, and all businesses will have an electrical transformer either on premises or very nearby, and this is how electricity gets from the generator to across the network and to your business. So the idea is that you're changing a voltage from low to high or high to low. And the reason we do this is because it is more efficient to transmit electricity at higher voltages, and we use electricity at lower voltages in order to, well, firstly it's safer, but also it's more practical to use for machinery. So what happens at higher voltages is that we have less current, but at lower voltages we have more current. And again, we'll detail that a bit more later in the presentation. So this is an example of our electricity network. So here we have our generating station, which has the moving, rotating magnet in a coil. Then we have our transformer, overhead lines, more transformers. So this transformer is moving the voltage up to 23,000 volts. The voltage here is maybe 5,000 volts. Then we get to a receiving station or substation, and from there our 23,000 volts probably drops to 132,000 or 66,000 volts. This example at 69. Then we get to a distribution substation where again the voltage drops perhaps to 12,000 volts. In the UK maybe 11,000 or 6,000 volts. And that is then delivered to commercial customers, industrial, and again to residential customers. So just to get a little example of that, this is a real example of a high voltage transformer. And just to give you a scale, this box is probably the height of a person. Should get a picture of a person here, but very significant machines where you have the electricity coming in and going out. Then overhead transmission lines. You'll be familiar with these pylons marching across the country. These are potentially 230,000 volt pylons. And what you have here is actually down one side you have one circuit, and on the other side a second circuit, and each circuit represents, each wire, you see 1, 2, 3, represents 3 phase, and we'll come back to that. Then this is an example of an electricity substation. So along the overhead lines you'll find across the country very large substations, which are effectively a distribution board for the country. So you may have multiple circuits coming into a substation and many more leaving the substation. It allows National Grid to be able to switch out an overhead line for maintenance and switch in another overhead line for maintenance, and also act as an interface to distribution network operators. So Northern Power Grid or Western Power may own half the site, so National Grid would supply the voltage in at high voltage, a transformer, and then your local distribution network operator would take that electricity and distribute it within the geographical region. Then certainly in rural areas we have wooden pole circuits. This could be 66,000 volts lines. Again, we have 1, 2, 3 phases, and these, as you say, are simple wooden poles distributing the electricity in rural areas. So small towns and villages may have their electricity delivered by such a pole. In urban areas, you may, admittedly this is a slightly old-fashioned building, a red brick building with electricity substation. Just to give you an idea of the scale, there may be 2 transformers in here. More modern ones tend to be much smaller red brick, much smaller building footprint. But I think, let's say back in the day, and when I say back in the day, I'd say 1930s perhaps, they certainly put a bit more architectural thought into electricity buildings. And finally, local pole mounted transformers. again, this transformer may in fact be for a small village. Even a farm may have what we call a pole mounted transformer. You may also see similar transformers in fenced off in more urban areas. So for example, every few streets may have a transformer connected. So your street and your neighboring streets, so 2 or 3 streets, may have their own transformer. So some electricity technical terms. We've already described a few, but let's elaborate or go into a bit more detail. Current and voltage. So when we say current, what we're referring to is amps. Amps is the flow of electrons, if you like, through an electrical conductor. And the more amps and the bigger the voltage, the more power is delivered. So our voltage is effectively as described here, the pushing energy or the level of force that could be applied to those electrons in order to get them going. So the bigger the voltage, the more current you get. And ohm is the resistance. So resistance is always trying to stop current, and resistance is used to best effect in electric heating. So effectively you apply a voltage to an electric heater, and the ohms is what gives off the heat. It's the resistance to the flow of current. And we have a very elegant law, Ohm's law, where the voltage equals the current times the resistance, or the voltage divided by resistance equals the current. So it's a simple 3-variable formula. So if you know 2, you can easily establish the third quantity. And this is a fundamental of electrical engineering. AC and DC. So AC is an alternating current. DC is direct current. So most higher energy use is on alternating, and most lower energy use is on direct. So examples of direct are typically any device that has a battery, because a battery is direct current. So if you imagine in your house, what would be on direct current would be computers, mobile phones, virtually anything that is primarily electronics. What you find on alternating current is primarily anything to do with heating or even lighting. So your electric oven would be on alternating, your toaster would be on alternating, your electric kettle would be alternating. So we use alternating primarily for the transmission of electricity because frankly that's how transformers work. Transformers rely on alternating current. We use, I'd say mostly or certainly more frequently recently with mobile phones and all sorts sort of tablet PC devices, direct current. But alternating is what comes into your house and you have to convert it to direct. Frequency. So if we think back to how electricity is generated, we have a rotation, and the speed of that rotation is the frequency of electricity. So we have in the UK a 50 Hertz electrical system. That means 50 times a second. So this wire is rotating 50 times a second between this magnet. So when you see a wind turbine rotating maybe once or twice a second, there's gears within the wind turbine, so the generator is actually turning at 50 times a second. Every single electrical generator, whether it's gas, nuclear, however, ultimately this rotation is 50 hertz or 50 times a second, and that's where we get our what we call our frequency or system frequency. So where is 50 hertz used? You can see from this sketch of the world, let's say the majority of certainly the surface area use a 50 hertz electrical system, whereas the Americas and I'd say most of South America are on 60 hertz. There's no distinct advantage in 50 or 50 hertz over 60 hertz. Mostly the reason is historic, and the main reason we're actually at 50 hertz is that originally electricity was used for lighting. If the frequency was much lower than 50 hertz, then when you look at a light bulb, and an old light bulb, not an LED but incandescent, you would actually see it flicker like a disco strobe light. So that's the reason it needs to be, let's say, at least 50, because otherwise the human could perceive flicker. Any faster than 50 or even 60 hertz, then you have mechanical problems with the machinery, because 50 hertz means 50 times a second. To have a big machine rotating faster has mechanical problems. So 50 hertz or 60 hertz was chosen as a suitable band to compromise between flicker and the mechanical issues of a big machine going that fast. So I've mentioned a couple of times already three-phase. So electrical generators generate what they call three-phase electricity, and that means for each rotation of the magnet that we get three individual current supplies. And the reason we have three-phase is simply that it's convenient to how it fits around the machine. So a very practical thing again, that two phases isn't enough because we'll have space for a third phase, but we don't have 4, 5 or 6, because then the machine gets too complicated to build, or realistically there isn't enough physical space around the machine to build three phases. So when you look at a pylon, one side of the pylon has what we call one circuit, the other side of the pylon the second circuit, but each of these wires is physically a separate connection all the way back to the generator. So it is phase 1, phase 2, phase 3, or red, green, blue, and there is different colors which I can't think of, brown, grey, blue perhaps, for denoting three-phase supply. And the reason we send three-phase supply is for industrial applications it delivers more power than a single-phase supply. Again, here's another example of the three phases. So when you see three cables, that's why it's how electricity is generated, always in threes. So power, real and reactive. So ultimately purpose of electricity is to deliver power, to light our homes, to heat our homes, to drive machinery. What we have here is the power triangle. So we have real power, reactive power, and apparent power. Now, a business pays directly for real power. They pay a penalty for reactive power, and what is delivered is apparent power. This is known as a power triangle. Now, normally this angle is called the power factor, and normally it's actually reversed. So the apparent power is normally below the real power, and the reactive power is what they call lagging. So what is that? A simpler explanation is, if you imagine a pint of beer, the real power is the substance. The reactive power is, I won't say unusable, because reactive power is required to provide an angle or a differentiator for electrical machines, but the net effect is the summation of the two to give the apparent power. Now, a better analogy that I like to use is a barge. So we have a poor horse here towing a barge. Now, if you imagine where would be the best place for the horse to stand. So if anybody's ever done a tug of war or anything like that, the most efficient place for that horse to stand will be directly in front of the boat. But because the tow path is obviously adjacent, that creates an angle between the barge direction and the horse. So for the horse, he can either move faster to move the barge at the same pace, or if he walks slower, then the barge will obviously go slower. So, or I should say, he needs to put more effort in to keep the barge going at the same pace, which is so his real power is coming along here. His apparent power is the speed of the barge, and his reactive power is the perpendicular to the barge. So the idea being that in electrical systems, we need to consider the angle between the work being done and the amount of work required to deliver it. Because unfortunately that is something that is charged to certainly high user businesses as a penalty. AC-DC converter. So a lot of you will be familiar with a mobile phone converter. So this converts AC, which is what comes out of a domestic socket, into a DC supply. So this converter is probably 240, 220 volts and converts it to, say, 5 volts to charge a mobile phone. And that's what's called an AC-DC converter. This is a much larger example of an AC-DC converter and is used on interconnectors from between the UK and France, and perhaps more recently even Norway. So we have AC around the UK, but for the cable we actually use DC because it's slightly more efficient to transmit at high voltage DC than high voltage AC. So across the cable of let's say however a couple of hundred kilometers is DC, but at either end we would convert it back to AC. So business electricity bill. So we've gone through some of the terms and just a brief understanding of how the electricity is distributed and, well, transmitted and distributed across the country. So if we consider electricity meters, so at your business, this is how you will be charged. Your humble electricity meter hidden in some cupboard, no doubt. And this is how your electricity is measured. And these are 3 different types of electricity meter. And your electricity is basically measured in kilowatt hours. So this is how many kilowatts you've used over per hour. And you could be charged, I don't know, 16 pence per kilowatt as an example. So from what we've talked about, First, within electricity bill, you have multiple charges, and included in this is what they call the distribution charges or distribution service charges. And there's multiple electricity distribution companies in the UK. For example, I'm living in number 5, which is Northern Power Grid. Big swathe of the country, number 7, Western Power, number 1, Scottish and Southern. So these are the businesses that are responsible for the physical connection to your premises. So everybody, home and business, should know your electricity distribution company, because if there's a problem with your supply, these are the people you call. So TUoS, distribution use of system charges, cost per kilowatt. So these are costs that are on top of your electricity costs, and there's a breakdown later, but suffice to say there's a cost you pay for your actual electricity, but on top of that you have TUoS costs and taxes and other costs. So these are time of day costs. So what you find is that it's broken down into red, amber and green charges. So our red charges, basically in this example between 4 and 7 p.m. and it does vary region to region, not by much, but certainly I think in London might have the more significant differences. But the idea here is to encourage people to use electricity in the green period and discourage people from using electricity during the red period. And you'll find the amber period is effectively when people are awake. So amber starts at 7 a.m. and finishes at 11 p.m. So this is where metering and understanding that if there's some electrical use your business is doing between 4 and 7, that you can move to between midnight and 7 a.m, then it would save you significantly on your TUoS charges. So distribution use of system charges. Now this may already be in place, but what they are trying to do, what they have required to be done, is level up the charging across the red, amber and green period. So currently red is charged significantly more, but what they're doing is trying to spread the cost from red into amber and green, and partly because it's reflecting that a lot of companies are already mitigating red charges by moving electricity usage to green, but also just to be fairer, because some businesses can't avoid using electricity in the red charges, and if it was felt that they were unfairly penalized. So you can imagine a restaurant who are open up the kitchens at 4 ready for dinner at 6, or hotels or whatever sort of business, there's very little they can do to not use electricity during the red period. Transmission. So transmission, for most in the UK, transmission is by National Grid. So we call it a transmission and distribution system. So in Scotland it's covered by Scottish and Southern and Scottish Power Energy Networks, and in Northern Ireland it's Northern Ireland Electric. And these are the businesses that are responsible to take the electricity from the generator or the wind farm or whatever it may be, and deliver it to each of the regions, to deliver it to the DNO. And similarly to the DNO, they have their own charges, transmission system of use charges, TUoS. And the transmission system charges are done slightly differently. The red, amber, green charges of the distribution are charged across the year, whereas the transmission are charged in what they call triads. So briefly, and there's a whole raft on this, but the triads are based on a business's average energy use on the 3 most electricity intensive days, or the peak electricity usage days, between November and February of a year, but must be separated by 10 days. So, and the time of day, I'll move on, make it more. So if we look at a normal day with 100 kilowatts each hour, so this business is using 100 kilowatts, so 100 kilowatt hours each hour, and this is their cost for TUoS charges. So £6 in green to £18 in red period. If we look at that during a triad day, and a triad only applies to the kilowatts used in a very particular half hour, that could be, for the same business, £4,000. So for half an hour electricity usage, you could be charged £4,000. So if your business had the ability to switch off all its electricity during these 3 triad days, then you could save significantly on your energy bill. It is well worth understanding that a bit more. There's too much detail to go into in this presentation, but suffice to say, certainly if you're on a half-hourly bill, i.e. you're billed every half hour, understanding when and where triads impact your business would be financially beneficial. So, breakdown of those costs that we talked about. So what we have here is a typical breakdown of an electricity bill. So we have VAT, different applicable to businesses, but cost of buying energy. So 35% of your bill is the actual cost of the electricity. The remainder are cost of government schemes, so such as renewable energy obligation or any sort of green tariff or green schemes. Operating costs, that is the cost of running the businesses or the billing businesses. So in the UK you can get your electricity from npower or any business. That's their operating costs. And then this 27% is the cost of the distribution system of use charges and the transmission system of use charges. So within your electricity bill, the amount you control is about half, because this is related to the amount of kilowatts you use, and this is related to the amount of kilowatts you use. So you need to consider moving electricity use and just energy efficiency. Similarly for gas, so gas supplied to a business, just to cover that topic. Almost 50% is the actual price of gas, whereas similarly cost of getting it to your home, this is the gas transmission system and distribution system. Then it's the operating profits of your supplier, and then government green schemes, profit and tax. So the vast bulk, the largest item for gas is the actual cost of gas. So just briefly on 2 commercial types of electricity bill. You have what they call a fixed electricity contract and a pass-through electricity contract. You can pause the screen and read the details, but in essence, a fixed contract sums all those charges together and provides you with a single rate. and that rate won't change during the term of your contract. So that rate will include the actual cost of electricity, your triad charges, your distribution charges, your government charges, all added up to give you a single rate of, say, 20 pence per kilowatt. Probably a bit high, but just an example. A pass-through electricity contract will give you a cost for the electricity at, let's say, 8 pence per kilowatt, but also detail the government charges, the TUoS charges, the transmission charges as separate line items on your bill, because regardless of the type of contract, it's your energy supplier that collects the money on behalf of the distribution company and the national grid company. But if they change their charges or the government decides different rates, if you're on a pass-through, that will directly affect your bill. If you're on fixed contract rates, you're fixed. So if any of that changes, your bill won't change. So if they go up or down, you have to pay the same price. On a pass-through, if they go up or down, your electricity bill will change. Now, the advantage there is if they go down, but chances are most of these costs go up. But on a fixed, chances are your electricity company has already factored in potential future price rises into your energy bill. So it's a balance of, do you take a direct risk on the energy prices, or is budget certainty more important to you? New technologies and development. So not a very long section. Just highlight some issues that businesses need to be thinking about. Number one is probably electric vehicle charging, because if you have even a small number of staff, you could be using a significant amount of energy or electricity to charge people's electric vehicles. What are you going to do about it? How are your staff going to charge their electric vehicles? Are you going to provide the infrastructure? For even a medium-sized office-based company, even 2 or 3 electric chargers could use more electricity than the business itself. So you need to think about this. Do you have the electrical infrastructure to actually connect staff EVs? Can you speak with your neighbor and agree a common EV parking policy? Even parking for a lot of businesses is a big issue. So parking and EV charging, something to think about very quickly. Solar panels have become very cheap, ideal for businesses that operate, frankly, during the day to reduce your energy bill. Also great for reducing your carbon footprint. There isn't that many advantages in exporting electricity at the moment, but that may change. The government have just announced by 2035 to be carbon neutral for electricity. So if you do have spare capacity, i.e. roof space or ground space to install solar panels, the rates that you get for exporting electricity may become better, because simply the government has to meet its 2035 carbon neutral policy for electricity. Maybe even you could sell directly to your neighbor. So if you have a big roof and your neighbor doesn't have a roof, if you install electric solar panels, make sure you cover yourself. Any surplus you could sell at a profit to your neighbor, who would be buying electricity a lot cheaper than from the grid. So you both could win if the economics work out. LED lights. At this stage, I'd say it's criminal for any business not to be LED lit. So do take a look at your lights next time. Winter is upon us. The nights are getting short now. So do start a rolling program of LED replacement or replacement to LED. Make sure you get a competent contractor though. The lighting lux levels, or the intensity of the light, does vary considerably between LED products, just to make sure you get the right product and that you meet your safety obligations, particularly if you're a school or any sort of public building. You need, even industrial buildings need minimum lighting levels at people's work area or study area. So a competent contractor will, you payback on LEDs is still fantastic. So it's really the hassle of swapping out awkward lights, really, but well worth it. Battery storage, it's the topic of the year, maybe that's a bit of an exaggeration, but we are, especially if you have a renewable technology for generating electricity, if you have a surplus, certainly storing it is a good option. At the moment, I'd say batteries, the cost benefit of batteries are difficult to justify. Certain applications may be different, but the capital cost of a sizable battery system is still very expensive, and it may not yet be the moment to go for it, but it may mitigate problems with EV charging. So if you have a large battery, you can charge up overnight and use that to charge staff cars during the day. That might be the right option for you. And then finally, just so I show, a lot of battery providers are repurposing older EV batteries. So basically taking the batteries out of an electric car after 2 or 3 years. They're still very good, maybe at 90% capacity, but because of range anxiety, drivers want to swap them out. They're actually installing them in businesses and homes. So if you have a Tesla, you may well have what they call a power wall, and basically charging overnight on the green charges and then using it during the red to save money on electricity bill. So again, it's an option, payback 5-6 years perhaps, maybe sooner, depending on what technology and how overall the government implements its 2035 target. And finally, but certainly not least, behavioral changes to drive energy efficiency. So when speaking about electricity use, or effectively talking carbon emissions, and the idea is that perhaps the biggest changes or the biggest reductions will come from behavioral changes of staff. So do consider on the left here we have an image of a system from Measure My Energy, this is, that actually monitors on a very granular level the electricity usage. So not just your electricity meter, but individual circuits or floors on your building or departments, and looks at their individual energy use. And from that you can say, well, why are you using electricity when nobody's in the building, or do you need to use so much energy between 4 and 6? What can we do about it? And also I've put up the logo for ISO 50001, something I'm very passionate about. It's the energy management standard. So from the same family as ISO 9001, which is the quality management system, or ISO 14001, the environmental management system, ISO 50001 provides the structure for continual improvement of energy use, be it electricity, gas, fossil fuels. However you use energy, it's a good template and a good management system to continually review and look to improve, and therefore reduce costs, reduce carbon impact from your business, whatever that process is or business actually undertakes. So I do have a number of additional training videos on YouTube if you click to type Bryce Energy Services. Just to highlight one or two, what is 1 ton of CO2, Pandora's box, maybe I need a better title, but basically explaining your business carbon footprint, your carbon footprint, a longer video helping you come up with a number for your carbon footprint, and supply chain. So understanding scope 3. So in order, I'd start with 1 ton, Pandora's box, supply chain, and then carbon footprint. So that's available on our Bryce Energy Services YouTube channel. So that's the end of that. 45 minutes. That was a very quick run through electricity for business, and it did touch on a lot of different topics and points, and feel free to drop me an email, info@bryceenergyservices.com, for more explanation or detail, but the intention was to give a broad overview to the topic. You'll also find us on LinkedIn, mentioned our YouTube channel and Twitter, and our webpage, bryceenergyservices.com. So thank you very much for your attention, and please do check out our other training videos. Thank you very much.